Good morning, 8th and 9th grade. This is part 2 of your science lesson for today. And I put the assignment on the board. If you see for today's assignment, 325 to 331 is the part that you will do, the page numbers. And then I had thought that we would complete it up to study guide, but I'm not going to do that. We will complete it then on Monday. So if you look at page 325, we're talking about the strong force. And look at, it's a nuclear force. If you look down at the bottom of the page, there's a man's name there that discovered this. Or, I don't know, yes, he discovered it. He was the first scientist that put this connection together. And I don't know how to say his name, but I'll give it a shot. Hideki. Hideki. And his last name, I won't even start there. I can dare to say that he is a foreigner for America. In 1949, he was awarded the Nobel Prize for Physics. So you see, this was not a dumb man, okay? He was brilliant. And what he actually did, in your atom, we talked about the protons and the neutrons in the center. Your electrons, let's say your electrons are flying around the outside here. And then right in the middle, you have your protons and your neutrons. And I'll just make little dots. I should make different colors, I guess, for protons and neutrons. But anyhow, he said there must be a connection in that nucleus that holds those together, because neutrons are neutral, you know, and the protons are positive charge. So he said there has to be something that's holding them together. And he called it, if you turn over to page 326, he called them PIons. Actually, the name is actually on the pronunciation is on 325. Down at the bottom, it's a black word there, PIons. He said there are little pions that are being exchanged between the nucleus, in between the protons and the neutrons. There's a little pions. They're exchanging pions, and that's what's holding the nucleus together. Otherwise, the nucleus would fly apart. Now, remember, we're working on an extremely small scale here. And he says they're just short-lived. They don't last long. They pass these little pions back and forth between each other, and they just disappear. They're a short period of a particle. Well, this is part of the strong force. The way we talk about the strong force is a nuclear part of it. And it's more, the strong force would be more known today as radioactivity. And that is, I put that word up here, radioactivity is isotope. It is when you have an atom that has a different number of neutrons than protons. Okay, so now follow this. Protons, the equal electrons, that will be always the same. So if you have 5 protons, you'll have 5 electrons. And a lot of times you'll have 5 neutrons, but not in the isotope atom. In the isotope atom, you have a different number of neutrons. And you can have that because they're neutral charge. They're not negative, they're not positive. So, in the radioactivity happens whenever you have a different number of neutrons in your isotope atoms. Now, radioactivity is known in 3 different forms, and it's the beta decay, you have the alpha decay, and the gamma rays. And each one of these is when the atom dysfunctions or does not function the way it should. If you look on page 328, you see a figure there, and I was going to try to put you on a video clip. You see there's a little CD up in the top of figure 13.5 there at the bottom, and that will show you the radioactivity of the beta and also the alpha decay. When you have the beta decay, that's whenever the atom breaks apart And you can see, it's the first example. You see that little beta particle down there in the bottom that's shooting down? It's throwing out a neutron. And when it throws out a neutron, that little beta particle works like a bullet. And you change the atom. It's no longer the same. And this little bullet goes flying to other cells and destroys other cells. It's like, it's hard to imagine when you think of it, but our bodies, other things around us, all matter is made up of tiny little cells. And remember, we can't see them with our eyes. So, this little bullet that it's shooting out, can you imagine how small it is? It is just, I don't even know how to tell you how small it is. It is just tiny, tiny. And that little bullet goes flying out and crashes into other cells and destroys other cells. Or most of the time it destroys them. If it doesn't destroy them, it will at least destroy the DNA in them. Now, when you go to the alpha, when the alpha decay, that is when there is a neutron and a proton form a second one. Now, you look at the second part of the thing, of the figure 13.5. The second part, you see there's a neutron and a proton that pull away from here, that pull out of here, out of the center, and they form another little particle. I think it shows 4 of them there. It is not like a particle, or like one single neutron shooting out in the beta decay, but in the alpha decay, there is actually a group of them. But anytime this happens, it changes the atom. No longer is it the same. When you take away some of the neutrons, and you can look on your periodic chart, anytime you change the number of protons and neutrons, it changes the atom. It's a different formula. On page 329, we'll give you the 3 different types of decay. It gives you each one, the beta decay, the alpha decay, and the gamma rays. And I won't read those. I'll let you talk about that. I'll let you read that. That way you can see the difference in the 3, because I've not talked about the gamma rays. I'll let you figure that out. Somebody's trying to call me. I don't know who they are, so I'll let them go. Now, if you go to page 330, you will find what is dangerous about this and how this works. If you see, there's a lot of talk about radioactivity being dangerous. Well, I'm telling you that it's not as much dangerous. Just from one person to the next person, there's radioactivity. So just being around people, there's radioactivity. That's really not dangerous. What is dangerous is whenever there is a large amount of it. Because just being close to people is not going to make it dangerous. There's not enough activity between 2 people to cause it to be dangerous. Go down to about 1, 2, 3, the 4th paragraph on page 330. It says, when produced as a result of radioactivity, alpha particles, beta particles, and gamma rays have a lot of energy. That's what is dangerous whenever they expose all that energy from the cell. They cause damage. Let me think about probably if any of you have been to a dentist, I know that whenever they take an x-ray of your tooth or of your mouth, they will put across you some kind of a heavy blanket. And it's heavy. It's real heavy when it lays on you. That is to protect you from those radioactivity rays that radiation does. Now, that's just one of them. If you look on on top of 331, it says, now don't be too scared here. They're not extremely dangerous. It takes millions, it says, and even trillions to destroy you. So just the rays that are passed back and forth from, well, the sun is another way that we get radioactivity, and that's the reason, one of the reasons when you're outside and you wear a hat, it protects you from the radioactivity waves of the sun. Keep moving on down. It talks about smoke detectors. Smoke detectors also put off radioactivity waves. Not enough, though, to be harmful to our health at all. It's way below the dangers of destroying us, because our bodies are continually making new cells, and old cells are dying or either being destroyed. As long as there's not a huge imbalance, it's not dangerous to our health. It says most people, at the bottom of 331, most people, however, will never be exposed to a large amount of radiation in a lifetime. They will never be faced with such a situation. So don't be too petrified. This person is still wanting to try to get a hold of me. It's never a serious threat unless you would work in an emergency room, or you would work someplace that would have high activity of radio waves. Just a normal life, you're in pretty good shape. Don't worry about that. So anyhow, I will finish up on 332. On the top of 332, you should do 13.9 on your own, plus the others behind. Have a good day.